Look up at the night sky for just a moment. Those glittering stars, those sweeping galaxies, they're all dancing to an invisible rhythm. But here's the thing, the universe has a hidden conductor, a silent force pulling strings behind the scenes. It twists the arms of galaxies into spirals, shields planets from deadly radiation, and even guides creatures across entire oceans without a single map. This isn't magic, it's magnetism on a cosmic scale. Magnetic fields are the universe's secret architects, shaping everything from the birth of stars to the jets screaming out of black holes. And today, we're uncovering 30 mind-blowing ways these invisible forces mold the cosmos. You'll see how magnetic fields control solar storms that could knock out power grids, how they light up the skies with auroras on distant worlds, and even how they might hold clues to dark matter itself. This is the hidden fingerprint of the universe, and by the end of this journey, you'll never look at the night sky the same way again. So buckle up, we're diving into the invisible web that holds the cosmos together. Now let's zoom in on our very own cosmic neighborhood, the Milky Way. Those stunning spiral arms you've seen in images aren't just swirls of stars and gas drifting aimlessly. They're sculpted by an invisible hand, magnetic fields. Picture these fields as cosmic scaffolding, stretching across tens of thousands of light years, guiding the flow of gas and dust like an unseen river current. Without them, galaxies might look more like messy blobs than the elegant pinwheels we know. Here's how it works. As a galaxy spins, its magnetic fields get stretched and twisted, forming a vast network that acts like a skeleton. This framework channels raw material, hydrogen gas and dust into dense, orderly lanes along the spiral arms. It's why star-forming regions often line up so neatly along these curves. The fields don't just organize the chaos, they amplify it. By compressing gas, they create the perfect nurseries for new stars to ignite, and we're not just theorizing. Radio telescopes have captured stunning evidence of these magnetic bones. Instruments like the Very Large Array have mapped the Milky Way's fields by detecting the way they polarize radio waves emitted by cosmic dust. The result, a ghostly blueprint of magnetic lines, crisscrossing the galaxy's arms like threads in a tapestry. Even more mind-blowing, some galaxies show fields strong enough to defy the pull of gravity, propping up their spiral structures against the universe's relentless tug toward disorder. But here's the kicker, these fields aren't static, they're dynamic, evolving with the galaxy itself. When galaxies collide, as the Milky Way and Andromeda will billions of years from now, their magnetic fields tangle and reorganize, reshaping their iconic arms in the process. It's a reminder that magnetism isn't just a background player, it's a master sculptor quietly shaping the grandest structures in the cosmos, and this is just the beginning. Because when we look deeper, we'll see how these same invisible forces don't just build galaxies, they bring stars to life. But that's a story for the next chapter. Now let's take a closer look at where the magic of star birth unfolds. Those vast glowing clouds of gas and dust you see in images of the Orion Nebula. They're not just pretty cosmic scenery, they're active construction zones, and magnetic fields are the unseen foreman directing the show. Here's the fascinating part. Gravity wants to pull all that gas and dust together to form stars, but magnetic fields push back, acting like cosmic bungee cords. Imagine a cloud of hydrogen gas collapsing under its own weight. As it shrinks, the magnetic field lines running through it get squeezed tighter and tighter, building up tension like a coiled spring. For a while, this magnetic resistance holds gravity in check, slowing down the collapse. It's a delicate tug of war between two invisible forces, one pulling inward, the other holding firm. But there's a breaking point. When the pressure becomes too much, the field lines suddenly snap, releasing their stored energy in a dramatic burst. This moment is like the universe flicking a switch. Gas rushes inward, temperatures skyrocket, and in the heart of that chaos, a new star ignites. Think of it as a cosmic pressure cooker finally letting off steam, and what comes out isn't just heat, it's light, energy, and the birth of something entirely new. The Orion Nebula is a perfect example. Telescopes have caught this process in action, revealing young stars still wrapped in their dusty cocoons, their birth fueled by the very magnetic fields that once held them back. And it's not just one or two stars, entire clusters form this way, with magnetic fields orchestrating the whole dance. Without them, gas clouds would collapse too quickly, leading to fewer, more massive stars. Instead, magnetism ensures a balanced stellar nursery where stars of all sizes get a chance to shine. What's even more incredible is how these fields leave their fingerprints. Polarized light measurements show the twisted, tangled paths of magnetic lines around newborn stars like footprints in cosmic snow. And sometimes those fields don't just fade away, they shape the star's future, influencing the disks of dust and gas that might one day become planets. So next time you gaze at a nebula, remember, you're not just seeing a cloud, you're witnessing a cosmic construction site with magnetic fields quietly calling the shots. And speaking of cosmic construction, wait until you hear how these same fields turn into explosive powerhouses when stars reach the end of their lives. But that's a story for another day. Now let's turn our gaze closer to home, where the sun's magnetic drama unfolds in spectacular fashion. Those beautiful loops and arches you see in solar images. They're not just decorative, they're ticking time bombs of stored energy. The sun's surface is a seething ocean of plasma, and its magnetic field lines are constantly twisting and tangling like overwound rubber bands. When these lines get too knotted up, they snap in violent outbursts we call solar flares, unleashing more energy than 1,000,000 volcanic eruptions. Here's how it works. Imagine stretching a slinky until it coils tighter and tighter. That's what happens to the sun's magnetic fields as swirling plasma drags them into complex shapes. These twisted lines trap charged particles, building up pressure like a cosmic pressure cooker. But there's a limit. When the tension becomes too great, the field lines explosively reorganize in a process called magnetic reconnection. In mere seconds, pent-up energy transforms into a blinding flash of X-rays and a torrent of high-speed particles. The most powerful flares can outshine the entire sun in certain wavelengths, even for minutes at a time. But the drama doesn't end there. These eruptions often hurl colossal clouds of magnetized plasma coronal mass ejections into space at millions of miles per hour. When one of these storms heads our way, Earth's magnetosphere takes the hit like a cosmic shield. The collision triggers dazzling auroras, painting the polar skies with shimmering greens and purples as solar particles spiral down magnetic field lines into our atmosphere. Yet there's a flip side. The same electromagnetic chaos can fry satellite electronics, knock out power grids, and even disrupt GPS signals. In 1989, a solar storm left 6 million people in Quebec without electricity for 9 hours, a stark reminder that we're tethered to our star's fiery moods. Scientists now track these magnetic tantrums using satellites like the Solar Dynamics Observatory, which captures ultra-high-definition footage of flares erupting. Their goal, predicting space weather like we forecast hurricanes, giving astronauts and power companies crucial warnings. Because while auroras might be nature's light show, the sun's magnetic explosions are a vivid reminder that even from 93 million miles away, its invisible forces shape life on Earth in ways we're only beginning to understand. And as we'll soon see, these fields don't just flicker on our sun, they sculpt some of the universe's most extreme objects. Now let's shift our focus from solar fireworks to the silent guardian standing between Earth and the chaos of space. What if I told you our planet wears an invisible force field? Earth's magnetosphere acts like a cosmic umbrella, constantly flexing and rippling as it deflects the sun's relentless solar wind. Picture this, a stream of charged particles races toward us at 1,000,000 miles per hour, only to be swept aside by our planet's magnetic embrace. These deflected particles curve around Earth in elegant arcs, tracing the shape of our magnetic protection like water flowing around a stone in a river. The secret lies deep within our planet. A churning ocean of molten iron in Earth's outer core generates this protective field through what scientists call the geodynamo effect. As the liquid metal swirls, it creates electrical currents that produce a magnetic field stretching thousands of miles into space. This field forms two crucial zones of protection. The Van Allen belts. Imagine these as giant donuts of trapped radiation encircling our planet, held in place by magnetic forces. The inner belt catches fast-moving electrons, while the outer belt snags protons from the solar wind. Together they form a buffer zone that absorbs and redirects harmful cosmic radiation. But not all worlds are so fortunate. Look at Mars, our rusty neighbor. Billions of years ago, Mars likely had a robust magnetic field and a thick atmosphere. Today, its field is patchy and weak. Without a global magnetic shield, the solar wind has stripped away most of Mars' atmosphere over time. What remains is less than 1% as dense as Earth's. This atmospheric erosion explains why Mars transformed from a potentially habitable world into the barren desert we see today. The difference couldn't be starker. While Earth's magnetic field preserves our life-sustaining atmosphere, Mars serves as a cautionary tale of what happens when planetary defenses fail. Back on Earth, our magnetosphere does more than block radiation. It creates spectacular auroras when solar particles sneak through near the poles. These glowing curtains of light are actually cosmic intruders getting funneled safely along magnetic field lines into our upper atmosphere. But the protection isn't perfect. During intense solar storms, some particles penetrate deeper, causing electrical disruptions. That's why understanding our magnetic shield isn't just scientific curiosity. It's planetary self-defense. Recent discoveries show Earth's magnetic field is always changing. The North Magnetic Pole drifts dozens of miles each year, and every few 100,000 years the poles completely flip. While this might sound alarming, fossil records show life has persisted through many such reversals. Our magnetic shield adapts. It weakens in some areas, strengthens in others, but never fully disappears. As we develop plans to send humans to Mars, this knowledge becomes crucial. Could we artificially create magnetic fields to protect future colonies? NASA has proposed placing a magnetic shield at Mars' Lagrange point to deflect solar wind. Early simulations suggest this might allow Mars' atmosphere to gradually thicken over decades. Earth's natural magnetic field gives us the blueprint. After all, it's kept our planet safe for billions of years. From deflecting solar storms to preserving our atmosphere, this invisible force proves that sometimes the most powerful protections are those we can't even see. Now let's journey from our protective magnetic bubble to one of the most extreme objects in the universe, where magnetism reaches unimaginable levels. Picture a collapsed star so dense that a teaspoon of its material would weigh 1 billion tons on Earth. Now amplify its magnetic field to 1,000 trillion times stronger than our planet's. This isn't science fiction. This is a magnetar, nature's ultimate cosmic powerhouse. These bizarre stellar remnants form when massive stars explode in supernova, leaving behind cores so compressed that protons and electrons merge into neutrons. What makes magnetars special isn't just their density, but how they spin. Imagine a ball of nuclear material rotating several times per second, dragging with it magnetic fields so intense they could erase credit cards from halfway across our solar system. These fields store staggering amounts of energy, twisting and snapping like overwound rubber bands until they release their pent-up force in devastating outbursts. The most spectacular displays occur when magnetars fire jets of particles at over 99% light speed. These aren't gentle streams but focused beams packing enough punch to distort spacetime itself around them. Scientists detect these events as sudden flashes of gamma rays, the universe's brightest electromagnetic explosions since the Big Bang. In milliseconds, a single magnetar can release more energy than our Sun will produce in its entire 10 billion-year lifetime. One particularly famous event occurred in 2004, when a magnetar 50,000 light-years away released a burst so powerful it temporarily ionized Earth's upper atmosphere. The explosion, called SGR 180820, delivered enough energy to our planet that some satellites actually shut down their instruments to avoid damage. All this from an object smaller than Manhattan. What powers these cosmic fireworks? It's all in the magnetic tangles. As the neutron star spins, its unimaginably strong magnetic field lines get wound up like spaghetti on a fork. Eventually, the tension becomes too great, and the lines snap and reconnect in violent events called starquakes. These abrupt rearrangements launch jets of electrons and protons along the star's magnetic poles, while also generating intense gamma rays. But magnetars don't just dazzle us with light shows. Their jets play a crucial role in seeding the universe with heavy elements. As the particles slam into surrounding gas clouds at relativistic speeds, they trigger nuclear reactions that forge gold, platinum, and uranium atoms. These same jets might also explain some mysterious deep space signals called fast radio bursts, brief but incredibly energetic blips that have puzzled astronomers for years. The wildest part, magnetars are essentially giant cosmic magnets with the mass of a star and the size of a city. Their existence proves that when it comes to magnetic fields, the universe always finds ways to outdo our wildest imaginations. From protecting life on Earth to launching starquakes across galaxies, magnetism shapes the cosmos in ways we're only beginning to understand. Now let's turn our attention from the explosive power of magnetars to something far more subtle, yet just as astonishing. Picture an invisible highway system spanning our galaxy, not for cars or spaceships, but for the fastest particles in existence. These are cosmic rays, atomic fragments racing through space at nearly the speed of light, and they're navigating the cosmos using magnetic fields as their guide rails. Galactic magnetic fields act like cosmic traffic controllers for these high-speed particles. Imagine throwing a handful of iron filings near a magnet. Instead of flying straight, they curve along the magnetic field lines. Cosmic rays behave similarly, spiraling along the Milky Way's magnetic pathways. But here's where it gets truly remarkable. Some of these particles carry energy so immense they make even the Large Hadron Collider look like a toy. Scientists call them ultra-high-energy cosmic rays, and they hold clues to some of the universe's most violent events. The most famous example, the Oh My God particle. Detected in 1991 over Utah, this single subatomic particle packed the kinetic energy of a baseball moving at 90 kilometers per hour. All that power concentrated into something smaller than an atom. How is that possible? The answer lies in galactic magnetism. These extreme particles likely originate from catastrophic cosmic events like supermassive black hole eruptions or colliding galaxies. Their journey to Earth involves being whipped around by magnetic fields for millions of light years, gaining speed like a surfer catching an endless cosmic wave. What makes galactic magnetism such an effective particle accelerator? It's all about scale and patience. Unlike human-built accelerators that push particles over short distances, cosmic rays get gentle but constant nudges from magnetic fields spread across thousands of light years. This process, called Fermi acceleration, works like a cosmic pinball machine. Particles bounce between magnetic shock waves in supernova remnants or active galactic nuclei, gaining a bit of energy with each collision over astronomical timescales. But galactic magnetism doesn't just accelerate these particles, it also scrambles their origins. By the time cosmic rays reach Earth, their paths have been twisted so thoroughly by interstellar magnetic fields that tracing them back to their sources becomes nearly impossible. It's like trying to find which raindrop in a hurricane filled your bucket. This cosmic detective challenge has led to ingenious solutions, like using entire galaxies as magnetic lenses or studying how cosmic rays interact with the cosmic microwave background. The impact of these magnetic highways extends far beyond astronomy. Cosmic rays constantly bombard Earth's atmosphere, creating cascades of secondary particles. Some theories suggest these interactions may influence cloud formation and even play a role in genetic mutations over evolutionary timescales, all made possible by the invisible hand of galactic magnetism shepherding particles across the void. From guiding the fastest particles in existence to hiding the locations of cosmic catastrophes, magnetic fields prove once again they're the unseen architects shaping our universe's most extreme phenomena. And as we'll soon discover, their influence stretches even further into the depths of space and time. Now let's journey from the cosmic highways guiding particles to one of the most dramatic displays of magnetic power in the universe, the relativistic jet screaming from black holes. Picture this, a supermassive black hole millions of times heavier than our Sun, not just swallowing matter but also flinging it outward in jets that stretch across entire galaxies. How does something known for its endless appetite also become the universe's most powerful slingshot? The answer lies in the invisible whirlpool of magnetism surrounding it. At the heart of every active black hole, there's a dynamo of unimaginable scale. As matter spirals inward, it forms a superheated disk glowing with intense radiation. But here's the critical twist: this disk isn't just hot gas. It's a swirling sea of charged particles, and where there's charge and motion, magnetic fields emerge. The black hole's rotation twists these fields into towering coils, like cosmic springs storing immense energy. When the tension becomes too great, the fields snap and reconnect, launching jets of plasma at nearly the speed of light. The most famous example, the jet from Galaxy Messier 87 or M87, captured in that groundbreaking Event Horizon telescope image. This jet isn't just impressive, it's a staggering 5,500 light-years long, powered by a black hole 6.5 billion times the mass of our Sun. The magnetic fields here are so strong they act like particle railguns, accelerating matter to speeds where Einstein's relativity comes into play. What we're seeing is essentially a cosmic particle accelerator stretching halfway across a galaxy. But how exactly do magnetic fields pull off this feat? It's a three-step cosmic dance. First, the black hole's spin drags spacetime itself into a whirlpool motion, a phenomenon called frame dragging. This twists the surrounding magnetic fields into helical structures. Next, the fields channel some of the infalling matter away from the event horizon, funneling it along the black hole's rotation axis. Finally, magnetic pressure and centrifugal forces hurl this plasma outward in tightly collimated beams. The result? Jets so precise they can drill through intergalactic space for millions of years without dispersing. These jets aren't just spectacular light shows, they're galactic sculptors. When they plow into surrounding gas clouds, they trigger shock waves that can jumpstart star formation or suppress it, depending on the circumstances. They redistribute heavy elements forged in stellar explosions across vast distances. Some theories even suggest that without these magnetic jets, massive galaxies wouldn't have grown to their current sizes, as the energy injection regulates their growth. What's truly humbling is realizing this isn't some rare phenomenon. Nearly every massive galaxy we've observed with a central black hole shows signs of these magnetic outbursts, either currently active or fossilized in radio bubbles. Our own Milky Way likely went through similar phases, with the Fermi bubble's giant gamma-ray structures above and below our galaxy being possible remnants of past jet activity. From shaping galaxies to seeding the cosmos with energy, black hole magnetospheres demonstrate once again that magnetism isn't just a side note in astrophysics, it's one of the universe's primary architects. And as we'll soon see, its influence extends even further, threading through the largest structures in existence. Now let's zoom from the colossal jets of black holes to the delicate artistry of magnetic fields weaving through the nurseries of stars. Imagine a cosmic tapestry, vast clouds of gas and dust not just drifting aimlessly, but sculpted into towering filaments like threads in a grand celestial loom. The most famous of these, the pillars of creation in the Eagle Nebula, those iconic columns where stars are born. But what holds these structures together against the chaos of space? The answer, once again, is magnetism's invisible hand. Here's how it works. In regions like the Eagle Nebula, gravity tries to pull gas and dust into dense clumps to form stars. But magnetic fields crisscrossing these clouds act like a scaffold, resisting gravity's pull and channeling material into long, rope-like filaments. Think of it like a spiderweb, thin strands that somehow hold their shape even as winds and radiation buffet them. The Herschel Space Telescope gave us proof of this, mapping far-infrared light to reveal how magnetic fields align dust grains along these filaments like compass needles. Without this magnetic scaffolding, these nebulae might collapse into stars too quickly, leaving no time for planets or life to emerge. The pillars of creation are a perfect example. Those towering structures aren't just pretty shapes, they're cosmic battlefields where magnetism and gravity duel. Magnetic fields running through the pillars help them withstand the eroding force of nearby massive stars' ultraviolet radiation. Meanwhile, inside the pillars, the fields guide gas flows, creating dense knots where new stars ignite. It's a delicate balance, too much magnetic resistance and star formation stalls, too little, and the cloud collapses chaotically. But the real surprise, these filaments are everywhere. From Orion's sword to the Vela molecular ridge, telescopes show interstellar gas isn't randomly distributed. Instead, it's organized into a vast network of magnetized threads, some stretching dozens of light years. This isn't just decoration, it's infrastructure. When two filaments cross, their magnetic fields can create shocks that trigger star formation, like cosmic traffic collisions birthing new solar systems. What's even more fascinating is how these fields leave their fingerprints. Polarized light waves vibrating in a preferred direction betrays the presence of magnetic fields aligning dust grains. Observations from Herschel and Alma show this polarization pattern matching filament shapes perfectly, confirming magnetism's role. It's as if the universe left us magnetic blueprints to decode. So next time you see those breathtaking nebula images, remember, you're not just looking at pretty gas clouds. You're seeing the universe's magnetic architecture in action, shaping star factories one filament at a time. And as we'll discover next, this magnetic influence extends even further, threading through the largest structures in the cosmos. Now let's take a journey beyond our solar system to a realm where magnetic fields paint the skies of distant worlds with otherworldly light. Imagine standing on an exoplanet, gazing up as its atmosphere dances with auroras, not in familiar greens and blues, but perhaps in ultraviolet or even X-ray hues, invisible to our eyes yet spectacular in their own right. While we've marveled at Earth's northern lights and Jupiter's colossal auroral rings, these phenomena aren't unique to our cosmic neighborhood. Across the galaxy, exoplanets with magnetic fields could be hosting their own dazzling light shows, and the clues are hiding in plain sight. Here's the science behind it. Auroras happen when charged particles from a star like our Sun's solar wind collide with a planet's magnetic field and atmosphere. On Earth, this creates the shimmering curtains we know, but scale this up to a planet like Jupiter with a magnetic field 20,000 times stronger than Earth's, and you get auroras so powerful they'd outshine our Sun if we could see them in visible light. Now apply that to exoplanets orbiting active stars, especially red dwarfs like those in the TRAPPIST-1 system. These stars are notorious for hurling violent stellar flares, bombarding their planets with intense radiation. If those planets have magnetic fields, they'd not only deflect some of that barrage, but also transform it into auroras on a scale we can scarcely imagine. The TRAPPIST-1 system offers a tantalizing case study. Its 7 Earth-sized planets orbit perilously close to their dim but tempestuous star. 3 of them sit in the so-called habitable zone where liquid water could exist. But habitability isn't just about temperature, it's also about protection. A robust magnetic field could shield these worlds from their star's fury while generating auroras far more intense than anything on Earth. Imagine a sky lit up by constant ultraviolet auroras, invisible to human eyes but detectable by telescopes. In fact, astronomers are already hunting for these signatures. By studying the light filtered through exoplanet atmospheres, they've spotted hints of auroral activity on gas giants like WASP-12b, where magnetic interactions might be heating the upper atmosphere to thousands of degrees. But rocky exoplanets could host auroras too. Take Proxima Centauri b, the closest known exoplanet to Earth. Its star, Proxima Centauri, is a flare-prone red dwarf that bathes the planet in radiation. If Proxima b has a magnetic field, even a weak one, it could produce auroras that paint its entire sky, not just the poles like on Earth. And here's the twist: some of these auroras might not even need a star. Planets orbiting pulsars, the ultra-dense, magnetized corpses of dead stars, could experience auroras powered by the pulsar's relentless particle beams, turning their skies into strobe lights of high-energy radiation. What's truly mind-blowing is how diverse these alien light shows could be. On a planet with a thick hydrogen atmosphere, auroras might glow in ultraviolet. On a world with a nitrogen-rich sky like Earth, they could pulse in blues and purples, and if magnetic fields are strong enough, they might even accelerate particles to such high energies that the auroras emit X-rays, something we've already seen on Jupiter. Telescopes like the James Webb Space Telescope are poised to spot these phenomena by analyzing exoplanet atmospheres for unusual emissions or polarization patterns that betray magnetic activity. So while we haven't directly imaged an exoplanet aurora yet, the pieces are falling into place. Magnetic fields don't just protect planets, they turn them into cosmic canvases, painting their skies with light forged in the battle between stellar winds and planetary shields. And as we'll see next, these magnetic fingerprints aren't limited to single worlds. They weave through entire galaxy clusters, knitting the universe together on the grandest scales. Now let's pull back the cosmic curtain to reveal how magnetic fields stitch together the largest structures in the universe: galaxy clusters. These sprawling metropolises of stars, gas, and dark matter are more than just random gatherings. They're interconnected by invisible magnetic threads that shape their evolution in extraordinary ways. Take Abell 2256, a galaxy cluster over 1 billion light-years away, where astronomers have witnessed what can only be called cosmic fireworks. Here, magnetic fields reveal themselves through a phenomenon called synchrotron radiation, a type of light emitted when electrons spiral at nearly the speed of light around magnetic field lines. The result: vast, glowing webs of energy that stretch for millions of light-years, painting the cluster in radio waves. These aren't just pretty patterns, they're cosmic fingerprints, showing us how magnetic fields influence everything from gas dynamics to cosmic ray acceleration on the grandest scales. What makes these magnetic webs so fascinating is their sheer power. In Abell 2256, the fields are strong enough to shape the behavior of the superheated gas between galaxies, known as the intracluster medium. This gas isn't just sitting idle, it's turbulent, stirred by the motions of galaxies and the energy of supermassive black holes at their cores. Magnetic fields act like cosmic rains, channeling this chaos into structured filaments and preventing the gas from dissipating into the void. Without them, galaxy clusters might look entirely different, less organized, less stable, and far less capable of holding onto their precious star-forming fuel. But the real showstopper is how these magnetic fields accelerate particles to near-light speeds. When galaxies collide within a cluster, a common event in these dense environments, shock waves ripple through the intracluster medium, compressing magnetic fields and supercharging electrons. This process, called Fermi acceleration, turns galaxy clusters into some of the universe's most powerful particle accelerators, far surpassing anything we could build on Earth. The synchrotron radiation we detect is the afterglow of this relentless cosmic turbulence. And here's where it gets even wilder. These magnetic webs might also trap cosmic rays, the ultra-high-energy particles that zip through space. Some theories suggest that galaxy clusters act as cosmic confinement chambers, with magnetic fields keeping these particles buzzing around for millions of years. This could explain why we see such intense synchrotron emission in places like Abell 2256. It's not just the fields themselves, but the trapped particles interacting with them over epic timescales. The story doesn't end there. Magnetic fields in galaxy clusters might even hold clues to dark matter. While dark matter doesn't interact with light or magnetic fields directly, its gravitational pull shapes the distribution of the intracluster medium and, by extension, the magnetic structures within it. By mapping these fields, astronomers can indirectly trace the invisible scaffolding of dark matter that holds the entire universe together. So the next time you picture a galaxy cluster, don't just think of it as a collection of stars. Think of it as a living, dynamic network bound together by invisible magnetic forces. And as we'll soon see, these forces don't just connect galaxies, they sculpt the very fabric of the cosmos, from the smallest plasmas to the largest structures we've ever observed. Now let's turn our attention to one of the universe's most spectacular recycling programs, cosmic magnet recycling. When massive stars reach the end of their lives, they don't just fade away quietly. They explode in a violent supernova, scattering their guts across space in a dazzling display of destruction and creation. But what's often overlooked is how these explosions don't just spread raw material. They also fling magnetic fields into the cosmos, seeding future generations of stars with their invisible influence. Take the Crab Nebula, the remnants of a supernova observed on Earth in the year 1054. This cosmic wreckage is more than just a beautiful swirl of gas. It's a living laboratory for understanding how magnetic fields persist and propagate after a star's death. Astronomers have studied the polarized light streaming from the Crab Nebula, and here's what's mind-blowing. That light tells us the nebula is threaded with powerful magnetic fields, remnants of the original star's core. These fields didn't disappear when the star exploded. They were amplified and stretched across light years, woven into the fabric of the expanding debris. This process is like cosmic composting. When a star explodes, its magnetic fields get tangled up in the ejected material, creating a magnetized soup that eventually collapses to form new stars. Think of it as the universe's way of passing the torch. Old stars die, but their magnetic legacy lives on in the next generation. Without this recycling, young stars wouldn't inherit the magnetic scaffolding they need to shape their birth and evolution. Here's where it gets even more fascinating. The Crab Nebula's magnetic fields aren't just passive leftovers, they're actively shaping the environment. The nebula's famous jets, those narrow beams of particles shooting from its central pulsar, are guided and collimated by these fields. They act like cosmic railroad tracks, channeling energy and matter with breathtaking precision. And because the pulsar, a rapidly spinning neutron star, is itself a powerhouse of magnetism, its influence intertwines with the nebula's inherited fields, creating a dynamic interplay that astronomers are still unraveling. But the real kicker, this isn't just happening in the Crab Nebula. Supernovae across the universe are doing the same thing, spewing magnetized material that becomes the building blocks for new stars and planets. Some of the iron in your blood, the calcium in your bones, even the oxygen you breathe, was forged in these explosions and carried across space by magnetic fields. So in a very real sense, you're connected to this cosmic recycling program. What's equally astonishing is how these fields might influence star formation itself. When a cloud of gas collapses to form a new star, the embedded magnetic fields can slow down the process, resisting gravity's pull like an invisible hand. This tension helps regulate how stars are born, preventing them from forming too quickly or too chaotically. Without these recycled fields, star formation might be a far more violent and unpredictable affair. So the next time you look up at the night sky, remember, those twinkling stars aren't just isolated points of light. They're part of a vast, interconnected web, linked by magnetic fields that have traveled across space and time, from dying stars to newborn ones. And as we'll see next, these fields don't just shape stars, they leave their mark on entire moons, planets, and even the possibility of life itself. Now let's journey closer to home, where a surprising discovery about our own moon reveals yet another layer of magnetism's cosmic influence. For decades, scientists assumed the moon was just a cold, lifeless rock with no magnetic field to speak of. But lunar rocks brought back by the Apollo missions told a different story, one that rewrote our understanding of Earth's closest neighbor. These rocks, some older than 3 billion years, contain tiny magnetic signatures locked within their crystals. That's right, the moon once had its own magnetic field, possibly even stronger than Earth's is today. So how could a world just 1% of Earth's mass generate such a powerful field? The leading theory points to a molten, churning core much like Earth's dynamo. Imagine a once fiery lunar interior with swirling liquid metal creating a magnetic shield that might have even protected a thin, early atmosphere. But here's the puzzle. Today, the moon's magnetic field is virtually non-existent. What shut it off? One possibility is that as the moon's core cooled and solidified, its dynamo engine sputtered out. Another clue comes from the timing. The field seems to have faded around the same time the moon's volcanic activity died down, hinting at a deep connection between its internal heat and magnetic life. This isn't just ancient history, though. NASA's upcoming Artemis missions aim to solve these mysteries by studying the moon's remaining magnetic traces in unprecedented detail. Future lunar landers might deploy magnetometers to map fossil fields frozen into the crust, revealing where and how long the dynamo persisted. Some scientists even speculate that pockets of molten metal could still exist deep underground, raising the slim chance of a dormant field waiting to be reawakened. Why does this matter? Because the moon's magnetic past could hold clues to other small rocky worlds like Mars or Mercury, where fields once thrived before disappearing. Understanding why lunar magnetism vanished might explain why some planets keep their shields and others lose them, with dramatic consequences for habitability. And here's a wild thought. What if early Earth's magnetic field was influenced by the moon's? The two worlds were far closer billions of years ago, and their magnetic interactions could have shaped everything from atmospheric retention to radiation levels. It's a reminder that magnetism doesn't just shape isolated objects, it connects them in ways we're only beginning to grasp. As we prepare to return to the moon, each new rock sample and magnetic measurement will peel back layers of this unsolved mystery. Who knows, the next chapter in lunar science might reveal that our quiet neighbor was once a far more dynamic world, its hidden magnetic heart still echoing through the dust of forgotten eras. And with that, we turn to an even bigger question: how did magnetism shape the very architecture of our solar system? Now let's zoom out to see how magnetism orchestrated the grand design of our solar system. The planets don't just orbit the sun at random, their paths are remarkably aligned, almost as if drawn on a flat sheet. This isn't just gravity's handiwork. The sun's magnetic field played a starring role in shaping this cosmic blueprint, and the secret lies in the ancient protoplanetary disk that once swirled around our newborn star. Picture the early solar system as a churning cloud of gas and dust with the young sun at its center. As this disk rotated, magnetic fields became frozen into the ionized gas, a phenomenon called magnetic flux freezing. These fields acted like invisible threads, channeling material into specific orbits and preventing chaos. Over time, the disk's magnetic tension forced particles to settle into a flat plane, much like pizza dough spinning into a uniform crust. But here's where it gets fascinating. The Sun's magnetic field didn't just flatten the disk, it also imprinted a sense of order on the planets themselves. As dust clumped into pebbles, then planetesimals, and finally planets, their orbits inherited the alignment of those primordial magnetic fields. This explains why all 8 major planets orbit in nearly the same plane, with even dwarf planets like Pluto only tilting slightly off course. Evidence for this magnetic sculpting comes from meteorites. Some contain tiny grains magnetized over 4 billion years ago, recording the direction of the Sun's early field. These cosmic time capsules confirm that the protoplanetary disk's magnetism was strong enough to steer planetary construction. Even today, remnants of this order persist. The Kuiper Belt's icy objects mostly orbit in the same flat plane, a distant echo of that magnetic scaffolding. Yet mysteries remain. Why do some exoplanet systems show wildly misaligned orbits? The answer might hinge on how strongly their stars' magnetic fields interacted with their disks. In systems where the star's rotation and magnetic axis were tilted, planets could end up in oblique paths, a stark contrast to our solar system's neat alignment. This magnetic choreography also had life-shaping consequences. By organizing debris into stable orbits, the Sun's field reduced catastrophic collisions, giving Earth a calmer environment to develop. Without this invisible guidance, our solar system might have been a chaotic jumble of crashing worlds, with no stable home for life to emerge. As we discover more exoplanetary systems, each one serves as a test case for how universal this magnetic blueprint truly is. Perhaps one day we'll find another disk where frozen in fields are crafting a flat, ordered family of worlds, a solar system not so different from our own, shaped by the same silent force that arranged our cosmic backyard. And with that, we turn to an even darker puzzle. Could magnetic fields hold clues to the universe's most elusive substance? Now let's venture into one of cosmology's greatest enigmas, dark matter. This invisible substance makes up roughly 85% of the universe's mass, yet it refuses to interact with light or magnetic fields as ordinary matter does. But what if magnetism holds hidden clues to its nature? Recent theories suggest magnetic fields might whisper secrets about dark matter through a hypothetical particle called the dark photon. Picture this: if dark matter particles carry a faint electromagnetic charge, unlike anything we've seen, they could generate ultra-weak magnetic fields as they move through space. These so-called dark photons would act as intermediaries, allowing dark matter to interact indirectly with regular magnetism. While undetectable by traditional telescopes, their influence might leave subtle fingerprints. One tantalizing hint comes from the Fermi Gamma-Ray Space Telescope, which has spotted mysterious gamma-ray excesses emanating from galaxy cores. Some scientists propose these high-energy flashes could be dark matter particles annihilating each other, with magnetic fields channeling the resulting radiation. The Milky Way center is a prime example. Its gamma-ray glow doesn't match known astrophysical sources, and the signal's distribution aligns eerily with predictions of dark matter density. Magnetic fields there could be funneling these emissions like cosmic lighthouses. Even more intriguing is how galaxy clusters, where dark matter is abundant, show sprawling magnetic structures. Could these fields be shaped by dark matter's gravitational pull, or even its phantom electromagnetic influence? Then there's the dark dynamo hypothesis. Just as Earth's spinning core generates our planet's magnetic field, some theorists suggest dark matter's motion might create ultra-faint magnetic realms in galaxies. These would be too weak to detect directly but could subtly alter how visible matter behaves. For instance, certain anomalies in cosmic microwave background data, the afterglow of the Big Bang, might reflect primordial magnetic fields influenced by dark matter's unseen hand. Of course, this remains speculative. Dark photons haven't been confirmed, and alternative explanations for gamma-ray excesses exist, like pulsars, but the quest continues. Upcoming experiments like CERN-S High-P aim to hunt for dark photons, while next-generation telescopes could map magnetism in galaxy clusters with unprecedented precision. If magnetic fields truly hold a key to dark matter, we might be on the brink of rewriting physics itself. And as we peer deeper into this shadowy puzzle, another magnetic marvel awaits: the universe's most precise timekeepers. Now let's turn our attention to one of nature's most reliable timekeepers, pulsars. These spinning neutron stars are the universe's metronomes, ticking with a precision that rivals atomic clocks. But what keeps them so steady? The answer lies in their incredibly strong magnetic fields, which act like cosmic brakes, slowing their rotation in a predictable way. Imagine a lighthouse beam sweeping across the ocean, but instead of light, it's a pulse of radio waves emitted by a city-sized star spinning hundreds of times per second. That's a pulsar, a dense remnant of a supernova, packing more mass than the Sun into a sphere just 12 miles wide. Its magnetic field, trillions of times stronger than Earth's, channels intense jets of radiation from its magnetic poles. As the star rotates, these beams sweep past our telescopes, creating the iconic pulse we detect. Here's where magnetic braking comes in. A young pulsar spins blisteringly fast, but its magnetic field acts like an anchor in space, transferring energy to the surrounding particles. This gradually slows the pulsar's spin, much like a spinning top loses speed due to air resistance. Over millennia, this slowdown happens at a near-perfectly predictable rate, allowing astronomers to use pulsars as celestial clocks. Some, like the famous millisecond pulsar, are so stable they lose just 1 second every 10 million years. This precision isn't just a cosmic curiosity, it's a tool. In 1977, NASA Voyager probes carried the golden record, a map to Earth using pulsar timings. Each pulsar's unique spin rate acts like a fingerprint, and their positions were plotted on the record as interstellar signposts. Future civilizations could theoretically use these pulses to locate our solar system. Just as sailors once relied on stars, today, pulsar timing arrays networks of radio telescopes tracking dozens of pulsars, are hunting for gravitational waves. Ripples in spacetime subtly alter the arrival time of pulses, offering a new way to detect cosmic collisions. Meanwhile, spacecraft like ESA's proposed Pulsar Nav mission aim to use pulsar signals for deep space navigation, eliminating reliance on Earth-based systems. But pulsars aren't just tools, they're cosmic laboratories. They're extreme magnetic fields reaching up to a quadrillion times Earth's. Let us test physics in conditions impossible to replicate. Some, called magnetars, unleash starquakes and flares so powerful they briefly outshine entire galaxies. Others, in binary systems, warp spacetime so severely they're helping refine Einstein's theory of general relativity. As we unravel the secrets of these magnetic timekeepers, another wonder calls the delicate dance of comets and their plasma tails, sculpted by the solar wind's invisible hand. Now let's shift our gaze from the precise ticks of pulsars to the graceful arcs of comets' celestial wanderers, whose tails are masterpieces painted by the solar wind's magnetic brush. When a comet nears the Sun, it doesn't just grow one tail but two, each shaped by invisible forces. One tail, made of dust, curves gently behind the comet like a golden trail. The other, a shimmering blue ion tail, streaks straight outward, defiant against the solar wind. But what creates this stunning duality? The answer lies in the magnetic fields woven through our solar system. Take Comet 67P, famously studied by the European Space Agency's Rosetta mission. As 67P plunged toward the Sun, its icy nucleus began to vaporize, releasing gas and dust. The Sun's ultraviolet light ionized some of that gas, stripping electrons and turning it into a plasma, a soup of charged particles. Here's where magnetic fields take center stage. The solar wind, a stream of charged particles racing from the Sun, carries with it the Sun's magnetic field. This field grabs the ionized gas and pulls it directly away from the sun, forming the ion tail's razor-straight beam. Meanwhile, sunlight itself pushes the uncharged dust particles, creating the softer, curved dust tail. The result, a cosmic work of art where physics becomes visible. Rosetta's close-up view of 67P revealed even more. The ion tail isn't just static, it's dynamic, sometimes disconnecting and reforming as magnetic reconnection events snap and realign the solar wind's field lines. Think of it like a kite string breaking in a gust only to be swiftly tied back. These disruptions can send bursts of plasma racing downstream, visible as bright knots in the tail. This interplay between comet and solar wind is so precise that scientists can actually map the solar wind's fluctuations by watching how comet tails behave, turning comets into natural solar probes. But the story doesn't end there. The solar wind's magnetic field also sculpts the ion tail structure. Under the right conditions, the tail can split into multiple filaments, each tracing a different magnetic pathway. It's as if the solar wind is braiding the comet's plasma, revealing the invisible architecture of space weather. And when a solar storm hits, the tail can light up with waves and knots, a direct imprint of the sun's fury. Comets like 67P aren't just pretty spectacles, they're classrooms. By studying their tails, we've learned how solar magnetic fields behave far from the sun, data crucial for protecting satellites and astronauts. Future missions might even use comet tails to sample the solar wind's composition, like dipping a cup into a cosmic river. As we marvel at these icy travelers, another magnetic marvel awaits: the explosive energy release of cosmic magnetic reconnection, where fields collide and unleash power beyond imagination. Now let's zoom in on one of the most explosive phenomena in the cosmos: magnetic reconnection. A process so powerful it's been called the universe's ultimate short circuit. Picture this: two opposing magnetic fields collide, snap like stretched rubber bands, and then explosively rearrange themselves, unleashing enough energy to power cities for millennia in a fraction of a second. This isn't science fiction, it's happening right now in Earth's magnetosphere and on the surface of the sun, shaping everything from dazzling auroras to solar storms that threaten our technology. Take Earth's magnetosphere, our planet's invisible magnetic shield. When the solar wind's magnetic field pushes against Earth's field, they don't just bounce off each other. Instead, their lines can break and reconnect, flinging charged particles at insane speeds toward our poles. The result, the northern and southern lights, those shimmering curtains of color that paint the night sky. But reconnection isn't just a light show. During intense solar storms, this process can overload power grids, knock out satellites, and even expose astronauts to dangerous radiation. In 2012, a solar storm narrowly missed Earth. Had it hit, experts estimate it could have caused trillions in damages. The sun, though, takes reconnection to a whole other level. Solar flares, those sudden bursts of brightness, are essentially the sun's magnetic field lines snapping and reconnecting near its surface. Imagine a twisted slinky suddenly untangling with enough force to vaporize entire planets. That's the scale we're talking about. The energy released heats plasma to tens of millions of degrees and accelerates particles to near light speed, creating X-rays and gamma rays. The biggest solar flare ever recorded in 2003 was so powerful it briefly overwhelmed sensors on spacecraft, even though Earth wasn't directly in its path. But here's the fascinating twist: reconnection isn't just destructive, it's also a cosmic delivery system. In star-forming regions, magnetic reconnection helps channel energy into newborn stars, and in distant galaxies, it may power the jets shooting from supermassive black holes. Even in labs on Earth, scientists are replicating this process to develop fusion energy, potentially a clean, limitless power source. NASA, a magnetospheric multiscale mission, 4 spacecraft flying in formation, has captured reconnection in action down to the electron scale, revealing how this universal process stitches together the cosmos. So next time you see an aurora or hear about a solar storm, remember, you're witnessing the aftermath of a cosmic collision between invisible forces, a reminder that even in the void of space, magnetism writes the rules. And speaking of cosmic rulebooks, let's turn now to the engines behind these vast magnetic fields, the spinning hearts of galaxies known as galactic dynamos. Now let's pull back the curtain on one of the universe's most powerful magnetic generators, the galactic dynamo. Deep in the heart of every spiral galaxy, including our own Milky Way, lies a cosmic engine that churns out magnetic fields strong enough to shape entire galaxies. Think of it like Earth's geodynamo, but scaled up to galactic proportions. Here's how it works. At the center of a galaxy, superheated gas and charged particles swirl around in a frenetic dance, driven by the rotation of the galaxy itself. This swirling motion acts like a giant dynamo, converting kinetic energy into magnetic energy and amplifying weak fields into colossal ones. Take the Milky Way's core, for example. Our galaxy's central black hole isn't just a gravitational monster, it's also surrounded by a maelstrom of magnetized plasma. As this plasma spirals inward, it twists and stretches magnetic field lines, creating a web of magnetism that extends thousands of light-years outward. These fields aren't just decorative, they play a crucial role in shaping the galaxy's structure. Observations from radio telescopes reveal how these magnetic threads weave through spiral arms, guiding the flow of gas and dust that eventually forms new stars. But here's where things get even more mind-bending. Some galaxies, like the nearby Andromeda, showcase magnetic fields that are bizarrely orderly, almost like a giant bar magnet stretching across the entire galaxy. Scientists suspect this uniformity comes from the dynamo effect operating over billions of years, smoothing out chaos into coherent patterns. Meanwhile, in more turbulent galaxies like Messier 82, magnetic fields are twisted into chaotic knots by violent star formation and supernova explosions, proving that dynamos can produce wildly different results depending on their environment. What's truly astonishing is the scale of energy involved. A single galactic dynamo can generate magnetic fields with energies equivalent to trillions of atomic bombs, all without a single wire or magnet. These fields then interact with cosmic rays, sculpting their paths and even influencing how galaxies evolve over time. For instance, without these dynamos, galaxies might not have the magnetic scaffolding needed to funnel gas into star-forming regions, potentially altering the very fabric of the cosmos as we know it. And just like Earth's geodynamo, these cosmic versions aren't static. They fluctuate, reverse, and even shut down under certain conditions. Studies of distant galaxies show that some have magnetic fields that flicker like candle flames, possibly due to changes in their central black hole's activity. Others, like the ancient galaxy class B 1152 plus 199, reveal that dynamos were already at work when the universe was just a fraction of its current age, proving magnetism's role as a foundational force in cosmic evolution. So the next time you gaze at the Milky Way's shimmering band across the night sky, remember, you're looking at the handiwork of a galactic dynamo, a hidden powerhouse weaving invisible threads of magnetism through the stars. And speaking of cosmic weavers, let's turn next to the mysterious ways magnetic fields guide life itself right here on Earth. Now, let's zoom in from the vastness of galaxies to something far closer to home, Earth's own magnetic miracles. While we've seen how magnetism shapes the cosmos, it also plays a starring role right here on our planet, guiding creatures in ways that seem almost supernatural. Take migratory birds, for instance. Every year, flocks like Arctic terns embark on journeys spanning tens of thousands of miles, navigating with pinpoint accuracy across featureless oceans and shifting landscapes. How they're tapping into Earth's magnetic field like an invisible GPS. Scientists have discovered that birds, sea turtles, and even some insects possess a built-in compass, a phenomenon called magnetoception. In birds, this likely involves tiny magnetic particles in their beaks or specialized proteins in their eyes that react to magnetic fields. Imagine a protein called cryptochrome, which gets activated by light and becomes sensitive to magnetism. This creates a sort of visual overlay where birds might literally see the magnetic field as patterns of light or color, guiding them effortlessly across continents. Sea turtles, meanwhile, hatch on beaches and immediately imprint on the local magnetic signature, using it years later to return to the exact same spot to lay their own eggs. It's like nature's version of saving coordinates in a map app, but here's where it gets even wilder. Some researchers believe quantum physics might be at play. The idea is that these animals exploit quantum entanglement, a bizarre phenomenon where particles remain connected across distances, to sense magnetic fields with extreme precision. In essence, a chemical reaction in their eyes or beaks could be influenced by Earth's magnetism at the quantum level, making their navigation not just biological but quantum biological. It's a theory still being tested, but if proven, it would mean life has been harnessing quantum mechanics long before humans even understood it, and it's not just about travel. Salmon use magnetic maps to return to their birth rivers, while honeybees rely on magnetic cues to orient their dances, which communicate flower locations to the hive. Even foxes seem to use Earth's magnetism when hunting, aligning their pounces along magnetic north-south lines for higher success rates. These behaviors suggest magnetism isn't just a tool for migration, it's woven into the daily survival strategies of countless species. What's truly humbling is how fragile this system is. Light pollution, for example, can disrupt birds' magnetic sensors, causing fatal disorientation during migration. And climate change is shifting magnetic landmarks as animals know them, forcing adaptations at breakneck speed. Understanding these mechanisms isn't just about solving a biological puzzle, it's about protecting ecosystems that rely on this invisible guidance. So the next time you watch geese flying in formation or a turtle vanishing into the waves, remember, they're not just following instinct. They're riding the same magnetic currents that shape galaxies, a cosmic connection linking the smallest creatures to the grandest scales of the universe. And speaking of connections, let's turn to how magnetism leaves its fingerprint on light itself, revealing secrets hidden in the glow of distant quasars. Now, let's stretch our gaze beyond our galactic neighborhood to the farthest reaches of the cosmos, where quasars act as cosmic lighthouses, piercing through the darkness with their brilliant light. What makes these distant powerhouses even more fascinating is how their light carries hidden clues about the magnetic tapestry woven between galaxies. When light from quasars travels billions of light years to reach us, it doesn't arrive unchanged. The journey through vast stretches of space leaves an imprint, a subtle polarization that twists the light's orientation. This polarization isn't random. It's shaped by the magnetic fields threading through the intergalactic medium, the sparse gas and plasma filling the voids between galaxies. Imagine these fields as invisible threads, gently bending the light like a cosmic filter. By studying this polarized light, astronomers can map these elusive magnetic structures, revealing a hidden framework that stretches across the universe. Here's how it works. Quasars, powered by supermassive black holes, emit intense beams of light. As this light passes through magnetized regions of space, the charged particles it encounters cause the light waves to align in specific directions, a process called Faraday rotation. The degree of polarization and how it shifts tells scientists about the strength and orientation of these intergalactic fields. It's like reading the universe's magnetic fingerprint. One of the most striking discoveries from this research is just how pervasive these fields are. They're not confined to galaxies or clusters but extend into the seemingly empty voids, suggesting magnetism is a fundamental feature of the cosmos. Some theories propose these fields were amplified by the turbulent motions of gas during the universe's youth, while others speculate they might be primordial, dating back to the Big Bang itself. Either way, they're sculpting the large-scale structure of the universe, influencing how matter clumps together into the vast cosmic web we see today. Polarized quasar light has even helped solve a long-standing mystery, the origin of diffuse gamma-ray glow in our universe. Scientists found that this glow aligns with regions where magnetic fields bend cosmic rays, confirming that these fields act as universal particle accelerators. Without them, the cosmos would lack some of its most energetic phenomena. What's next? Telescopes like the Square Kilometre Array are poised to take this research further, mapping intergalactic magnetism with unprecedented detail. These observations could finally answer whether these fields were present at the dawn of time or emerged later, shaping the universe as we know it. So, the next time you look up at the night sky, remember, even the light from the most distant quasars is whispering secrets about the invisible forces knitting the cosmos together. And speaking of whispers, let's turn to a planet where magnetism has gone curiously silent, Venus, and the puzzle of its missing magnetic shield. Now, let's shift our focus to a mystery much closer to home, Venus, Earth's so-called twin, but with one glaring difference. While our planet boasts a protective magnetic shield, Venus seems to have left its defenses at the door. Despite being similar in size and composition to Earth, Venus lacks a global magnetic field, and scientists have been piecing together why this neighboring world fell short. The key lies in the engine that powers Earth's magnetism, the geodynamo. Deep within our planet, the churning of molten iron in the outer core generates a magnetic field through a process called convection. But Venus, for all its similarities, doesn't have this same dynamo at work. One leading theory points to its sluggish rotation. A day on Venus lasts longer than its year, 243 Earth days to complete a single spin. That's achingly slow compared to Earth's 24-hour whirl. Without that rapid rotation, the convective currents in Venus's core may never have gained enough momentum to kickstart a self-sustaining magnetic field. Another piece of the puzzle is Venus's lack of plate tectonics. On Earth, the movement of tectonic plates helps regulate heat flow from the core, keeping the dynamo active. Venus's stagnant lid crust, however, might act like a thermal blanket, trapping heat and preventing the core from cooling efficiently. Without that temperature gradient, the convection needed for magnetism could have sputtered out long ago. But here's the twist: Venus isn't entirely magnetic field-free. Weak, patchy fields have been detected, likely induced by interactions with the solar wind. As the sun's charged particles bombard Venus's upper atmosphere, they create a flimsy, external magnetic layer, a far cry from Earth's robust shield. This leaves Venus's atmosphere exposed, explaining why it's slowly being stripped away by solar radiation, a stark contrast to Earth's preserved skies. Could Venus have once had a magnetic field? Some researchers think so. Evidence from ancient volcanic rocks, if ever sampled, might reveal traces of past magnetism, hinting at a more active core billions of years ago. Others speculate that Venus's thick, suffocating atmosphere, 90 times denser than Earth, somehow suppressed its dynamo, though the mechanics remain hazy. The mystery of Venus's missing magnetism isn't just academic. It's a cautionary tale about how delicate the balance of planetary habitability can be. Without that protective field, Venus transformed into a scorching, inhospitable world, a reminder of how crucial magnetism is in shaping a planet's destiny. And as we uncover more about our sister planet's secrets, we're forced to wonder, what other cosmic surprises are hiding in plain sight? Speaking of surprises, let's turn our attention to the oldest magnetic whisper of all, the faint imprint left by the universe's birth. Now, let's rewind the cosmic clock to the very beginning, back when the universe was a seething, newborn entity. Among the echoes of the Big Bang itself, there's a whisper, something subtle yet profound, hidden in the afterglow of creation. The cosmic microwave background, or CMB, is more than just a relic of the universe's infancy. It's a snapshot, a frozen moment in time from when the cosmos was a mere 380,000 years old. And within this faint glow, scientists are hunting for something extraordinary, the fingerprints of primordial magnetic fields. These aren't the magnetic fields we see today, sculpting galaxies or shielding planets. These are remnants from the universe's first moments, possibly forged during cosmic inflation, that explosive expansion that stretched space itself in a fraction of a second. If they exist, these ancient fields would have left a unique signature in the CMB, subtly polarizing its light in ways we're only beginning to understand. Enter the Planck telescope, a cosmic detective that mapped the CMB with unprecedented precision. Its data revealed puzzling anomalies, patterns in the polarization of light that don't quite fit our standard models. Some researchers believe these irregularities could be the work of primordial magnetic fields woven into the fabric of space during inflation. Imagine these fields as cosmic threads, stretched and tangled as the universe expanded, leaving behind faint but detectable imprints. But how could such fields form so early? One theory suggests they were birthed by quantum fluctuations during inflation, amplified to cosmic scales as space ballooned. Another proposes they emerged from the violent phase transitions of the early universe, like cracks forming in freezing ice. Whatever their origin, detecting them would rewrite our understanding of the universe's magnetic blueprints. The challenge, of course, is separating this signal from the noise. The CMB is a crowded canvas with contributions from everything from interstellar dust to distant galaxies. Yet, if we can tease out these primordial whispers, they'd offer more than just proof of ancient magnetism. They'd provide clues about inflation itself, testing theories about how the universe grew from a quantum speck to the vast cosmos we see today. And here's the tantalizing part. If primordial fields exist, they might still be with us, woven into the large-scale structure of the universe, subtly shaping galaxies and galaxy clusters in ways we're only starting to uncover. The Planck data is just the beginning. Future missions like the proposed LightBird satellite or next-generation ground-based telescopes could sharpen our view, peeling back layers of cosmic history to reveal whether these magnetic ghosts from the dawn of time are real. For now, the hunt continues, a cosmic game of hide and seek with the universe's oldest secrets. And if we find them, it won't just be a discovery about magnetism. It'll be a window into the very first moments of everything, a glimpse of the forces that set the stage for all that followed. Speaking of forces, let's turn to another magnetic marvel, one that doesn't just shape the cosmos but protects our own backyard. Now, let's shift our gaze closer to home, where the sun's magnetic drama unfolds in ways that directly impact us. The sun isn't just a steady ball of light, it's a seething, dynamic beast, with its magnetic fields constantly twisting, snapping, and unleashing storms that ripple across the solar system. And just like meteorologists predict hurricanes, scientists now forecast these space weather events, using the sun's magnetic activity as their guide. At the heart of this forecasting lies the sun's ever-changing magnetic field. Imagine the sun's surface as a bubbling cauldron, with magnetic field lines rising, tangling, and sometimes violently reconnecting. When these lines snap, they release staggering amounts of energy in the form of solar flares, explosions brighter than 1,000,000 atomic bombs. But the real troublemakers are the coronal mass ejections, or CME, colossal clouds of magnetized plasma hurled into space at millions of miles per hour. If one of these storms heads toward Earth, the consequences can be serious. That's where space weather forecasting comes in. Agencies like NASA and the National Oceanic and Atmospheric Administration, or NOAA, monitor the sun around the clock using satellites like the Solar Dynamics Observatory and the Deep Space Climate Observatory. These instruments track sunspots, dark, magnetically active regions on the sun's surface, measuring their size, complexity, and potential for eruption. By studying these magnetic hotspots, scientists can predict solar storms days before they happen, giving us crucial time to prepare. Why does this matter? For astronauts, a severe solar storm is a life or death concern. Outside Earth's protective magnetosphere, they're exposed to deadly radiation from these events. Forecasting allows missions to the International Space Station or future lunar expeditions to take shelter or delay spacewalks. Down on Earth, our power grids are equally vulnerable. A major tsunami striking our planet could induce powerful electric currents in power lines, frying transformers and causing widespread blackouts. In 1989, a solar storm knocked out Quebec's grid for 9 hours, leaving millions in the dark. Today, with forecasts, utilities can temporarily shut down vulnerable systems to prevent damage. But forecasting isn't just about disaster prevention. It also unlocks the sun's secrets. By linking specific magnetic field configurations to solar flares and tsunamis, scientists are piecing together the physics behind these eruptions. Recent breakthroughs in artificial intelligence are helping machine learning algorithms analyze vast amounts of solar data, spotting patterns humans might miss. The goal: to predict storms with the same accuracy as terrestrial weather forecasts. So the next time you check the weather app, remember there's a parallel forecast happening above us. The sun's magnetic fields don't just light our days, they shape the invisible tempests that swirl through space, and thanks to cutting-edge science, we're learning to navigate them. Now, let's journey beyond our solar system to a place where magnetic mysteries take on an even grander scale. Now, let's venture beyond our solar system to a realm where magnetic fields might be hiding secrets beneath icy shells. Around distant gas giants, moons like Jupiter's Europa or Saturn's Enceladus have already shown us the tantalizing possibility of subsurface oceans. But what if some exomoons, moons orbiting planets in other star systems, also harbor hidden oceans, their presence betrayed by the subtle tug of magnetic fields? Here's how it works. When a moon orbits within the magnetic field of its host planet, the salty water beneath its icy crust can act like a conductor, generating a secondary magnetic field through induction. Think of it like stirring a cup of coffee with a spoon. The motion creates swirls, and in the same way, the moon's movement through the planet's magnetic field stirs up electric currents in its ocean. These currents then produce their own magnetic signature, one that future telescopes might detect even from light years away. Europa is our prime example. Jupiter's powerful magnetic field sweeps over this icy moon, and measurements from the Galileo spacecraft revealed fluctuations that strongly suggest a global, salty ocean beneath its frozen surface. If Europa were an exomoon orbiting a distant gas giant, the same principles would apply. Advanced instruments like those planned for the European Space Agency's Jupiter Icy Moons Explorer mission or NASA Europa Clipper could one day be adapted to study exomoons, hunting for those telltale magnetic whispers. But why stop at our solar system's backyard? Imagine an exomoon twice the size of Europa, orbiting a warm Jupiter-like planet in the habitable zone of its star. Its subsurface ocean, kept liquid by tidal heating, could generate an even stronger induced field. Future observatories like the proposed Large Interferometer Space Antenna or ultra-sensitive radio telescopes might pick up these faint signals, giving us our first indirect evidence of alien oceans and potentially habitable environments beyond Earth. The implications are staggering. Magnetic fields could become our roadmap to finding life supporting worlds where traditional methods fall short. After all, light from distant stars makes spotting small exomoons directly nearly impossible, but their magnetic fingerprints. Those could be our cosmic breadcrumbs. So while we haven't found a magnetized exomoon yet, the physics is on our side. And as our tools grow sharper, we might soon uncover a hidden universe of liquid water, all thanks to the silent, persistent hum of magnetic fields. Next, we'll dive into another cosmic mystery where magnetism takes center stage, the colossal Fermi bubbles erupting from our galaxy's heart. Now, let's turn our attention closer to home, or rather, the center of our galaxy, where a pair of colossal structures defy explanation. Rising tens of thousands of light-years above and below the Milky Way's disk, the Fermi bubbles are two vast orbs of superheated gas glowing with gamma rays like cosmic lanterns. But what carved these mysterious bubbles into the fabric of our galaxy? The answer might lie in the interplay between our supermassive black hole and its magnetic fury. At the heart of the Milky Way, Sagittarius, a star, a black hole 4 million times the mass of our Sun, sits relatively quiet today, but evidence suggests it wasn't always so placid. Around 5 million years ago, it likely erupted in a cataclysmic outburst, devouring nearby gas and dust. As material spiraled into the black hole, its immense magnetic fields twisted into tight coils, channeling some of the infalling matter into jets shooting outward at nearly the speed of light. These jets, packed with charged particles and wrapped in magnetic energy, could have punched through the galaxy's gas, inflating the Fermi bubbles like balloons. Here's where magnetism's role gets fascinating. Gamma-ray telescopes reveal that the bubble's edges shimmer with synchrotron radiation, a telltale sign of electrons spiraling around magnetic field lines. This implies the bubbles aren't just hot gas, they're magnetized structures, their particles accelerated by shock waves from the ancient eruption. Imagine a pot of boiling water where heat creates rising bubbles. Now replace the water with magnetized plasma and the heat with a black hole's wrath, and you've got the Fermi bubbles, but the story doesn't end there. Recent observations hint at even older, fainter bubbles nested within the visible ones, suggesting Sagittarius, a star, might have had multiple outbursts over eons. Each explosion could have stacked like layers of an onion, with magnetic fields preserving their imprint. It's a cosmic echo of the black hole's temper tantrums, frozen in time. What does this mean for our galaxy? These bubbles are more than just a spectacle, they're a feedback mechanism. By venting energy and magnetic fields into the galactic halo, they might regulate star formation and even shape the flow of cosmic rays. And while we've spotted similar structures in other galaxies, the Fermi bubbles offer a front-row seat to study how black holes and magnetism sculpt their homes. As we peel back the layers of this mystery, one thing is clear: magnetic fields don't just shape the cosmos quietly. Sometimes they roar, and with next-generation telescopes like the Cherenkov Telescope Array poised to study these bubbles in unprecedented detail, we're on the verge of uncovering even more about their explosive origins. Next, we'll explore another cosmic puzzle where magnetism takes a surprising turn, the elusive hunt for magnetic monopoles. Now, let's shift gears to one of the most tantalizing what-ifs in physics, the cosmic detective story of magnetic monopoles. If you've ever played with a magnet, you know it always has two poles, a north and a south, inseparable no matter how many times you break it apart. But what if that wasn't the case? What if single, isolated magnetic poles, monopoles, existed? This idea isn't just a thought experiment. It's a missing piece in our understanding of the universe's fundamental forces. The concept of magnetic monopoles emerges from grand unified theories, ambitious frameworks that attempt to merge electromagnetism with the strong and weak nuclear forces. These theories predict that in the extreme conditions just after the Big Bang, spacetime itself could have sprouted defects like cracks in cooling ice where single magnetic poles condensed out. If they formed, these monopoles would be staggeringly dense, possibly as massive as a quadrillion protons, and carry a magnetic charge that defies our everyday experience. So why haven't we found them? The absence of monopoles is actually a paradox. Early universe calculations suggested they should be as common as protons, yet not a single confirmed detection exists. This discrepancy led physicist Paul Dirac to propose that monopoles might be hiding in plain sight. Their rarity explained by cosmic inflation, a fraction of a second expansion of the early universe that could have diluted them to near non-existence. Imagine searching for a single grain of sand scattered across all of Earth's deserts. That's the scale of the challenge. Efforts to spot monopoles have been creative, to say the least. Scientists have scoured moon rocks, deep-sea sediments, and even ancient mica crystals for traces of these particles, which would leave telltale trails of ionized atoms. Experiments like the Mo-Edel detector at CERN use super-sensitive materials to catch monopoles that might be produced in particle collisions, while cosmic ray observatories scan the skies for monopoles raining down from space. So far, silence, yet the hunt matters because monopoles aren't just curiosities, they're potential keys to deeper truths. Their existence would explain why electric charge comes in fixed units. Dirac showed this mathematically and could reveal hidden symmetries in the cosmos. Some theories even suggest monopoles might catalyze proton decay, a process that could rewrite particle physics. For now, magnetic monopoles remain ghostly what-ifs, their absence as intriguing as their hypothetical presence. But with experiments growing ever more precise, we might one day uncover whether these solitary poles are cosmic phantoms or relics waiting to be found. Up next, we'll witness magnetism's creative side as infant stars sculpt their nurseries with dazzling plasma jets. Switching our gaze from elusive cosmic particles to the dazzling spectacle of star birth, let's zoom in on the fiery tantrums of young stars. These celestial infants don't just quietly gather material to grow, they announce their presence with spectacular plasma jets, nature's own blowtorches carving paths through the chaos of their nurseries. Take HH34, a stellar toddler just 1,500 light-years away in Orion. Here, a protostar barely a few 100,000 years old is already flexing its magnetic muscles, shooting twin jets of ionized gas at speeds topping 1 million kilometers per hour. These jets aren't random outbursts, they're precision tools sculpted by magnetic fields. As the baby star spins, its magnetic field lines act like cosmic spaghetti, twisting and tangling as they funnel material from the surrounding disk onto the star's surface. But here's the catch: the star can't swallow all that gas. Like an overfilled cup, the excess gets violently ejected along the star's rotation axis, channeled by those same magnetic fields into narrow, collimated beams. The Hubble Space Telescope has captured these jets in breathtaking detail, revealing glowing shockwaves where the plasma rams into slower-moving gas, lighting up like cosmic neon signs. But why does this matter? These jets solve a star's growing pains. Without them, the protostar's rapid spin would fling material away, stunting its growth. The jets act as release valves, carrying away excess angular momentum, essentially letting the star spin down so it can keep feeding. Meanwhile, the outflows bulldoze cavities in the surrounding gas cloud, clearing the neighborhood for future planets. Imagine a construction crew blasting away debris before laying a foundation. That's what these jets do on a cosmic scale. The magnetic choreography doesn't stop there. Recent ALMA telescope observations show how these fields also shape the jet structure, creating helical patterns akin to DNA strands. A hint that magnetism might even influence the orientation of forming planetary systems. And when multiple stars are born together, their competing jets can sculpt entire nebulas into surreal landscapes, like the fingers of gas in the Carina Nebula. What's truly mind-bending is how these tiny stellar tantrums echo across the universe. The same physics powering HH34 modest jets also operates in supermassive black holes, whose relativistic jets shape galaxies. It's a reminder that magnetism scales effortlessly from star-forming clouds to the cosmos' largest structures. Next time you gaze at Orion's sword, remember hidden in that glow are stellar newborns, their magnetic fireworks quietly preparing the stage for worlds yet unborn. Speaking of cosmic prep work, our next stop reveals how magnetic threads weave galaxies into grand designs. Now let's unravel a cosmic dance where magnetism plays matchmaker between galaxies. Picture the Whirlpool Galaxy, also known as Messier 51, locked in a gravitational tango with its smaller companion, NGC 5195. Their swirling arms aren't just shaped by gravity, they're sculpted by an invisible magnetic handshake stretching across 25,000 light-years of interstellar space. Radio telescopes like the Very Large Array have mapped M51's magnetic field lines, revealing how they trace the galaxy's spiral arms with eerie precision. But here's the twist. These fields aren't just passive decorations. As the smaller galaxy tugs at M51 during their close encounters, it stirs up interstellar gas like a spoon swirling cream in coffee. This motion, called differential rotation, stretches and amplifies the magnetic fields, wrapping them tighter around the spiral arms. The result: magnetic fields become cosmic reinforced, channeling gas flows and even helping compress matter to trigger new star formation along the arm's crests. What makes this duo extraordinary is their magnetic conversation. The smaller galaxies' gravitational punches generate shockwaves that ripple through M51's disk, creating kinks in its magnetic architecture. These distortions then act like cosmic traffic cops, redirecting ionized gas flows and creating bright knots of star birth visible in Hubble images. It's a feedback loop. Gravity distorts the fields guide the gas, and the gas lights up as new stars, revealing the hidden magnetic blueprint. This interstellar waltz has broader implications. Similar magnetic interactions may explain why some galaxies like M51 develop such textbook-perfect spirals, while others remain flocculent or irregular. The fields essentially act as galactic glue, organizing chaos into structured patterns. Even more intriguing when galaxies eventually merge, as these two will in a few 100 million years. Their entangled magnetic fields may seed the next generation of stars in the resulting hybrid galaxy. So the next time you see an image of the Whirlpool Galaxy, look beyond its visual beauty. Those spiral arms are cosmic crime scenes, with magnetism leaving fingerprints on every star-forming region. And remember, this isn't just happening in M51. Across the universe, invisible magnetic threads are quietly orchestrating the grand ballet of galaxy evolution. Now let's turn our attention to a cosmic phenomenon that proves even magnetic fields have their own rhythm. Stellar magnetic cycles. Take our own Sun, for example. Every 11 years, like clockwork, it undergoes a dramatic transformation. Its magnetic field doesn't just weaken or strengthen, it completely flips poles. North becomes south and south becomes north. This isn't just a curious quirk, it's a process that reshapes space around the star, with real consequences for any planets in its orbit. During this cycle, the Sun's magnetic activity peaks in what we call solar maximum. Sunspots multiply, solar flares erupt more frequently, and the star's magnetic influence stretches farther into space. Then, as the poles reverse, everything calms down again. But here's where it gets fascinating. This cycle doesn't just affect the Sun. Stars across the universe have their own magnetic personalities, some with cycles lasting years, others decades. And these shifting fields don't just alter the star itself, they redefine the boundaries of habitability for any orbiting planets. Imagine a world nestled in what we'd normally call the habitable zone, where liquid water could exist. If its host star's magnetic field suddenly intensifies, that planet might find itself bombarded by deadly radiation and stellar winds, stripping away its atmosphere. On the flip side, a weaker magnetic phase could leave the planet vulnerable to cosmic rays from deep space. The habitable zone isn't just about distance, it's a delicate balance shaped by these ever-changing magnetic forces. We've seen this play out with stars like Tau Boötis, a system where the star's magnetic field flips every few years much faster than our Sun's cycle. Or take HD 753, a star with a magnetic cycle so extreme it causes wild swings in X-ray output, potentially sterilizing any nearby planets during its active phases. These discoveries force us to rethink what makes a planet truly livable. A world might sit in the perfect spot for liquid water, but if its star's magnetic mood swings are too violent, life may never get a foothold. This variability isn't just a modern discovery, Ancient records of sunspot observations, like those from Chinese astronomers over 2,000 years ago, hint at how these cycles have fascinated humans for millennia. Today, telescopes like the Kepler Space Telescope and the upcoming Square Kilometre Array are helping us map magnetic cycles in distant stars, revealing just how common and how diverse these cosmic rhythm shifts really are. So the next time you hear about a newly discovered exoplanet in the habitable zone, remember, its fate might not just depend on distance. The invisible ebb and flow of its star's magnetic fields could be the real deciding factor in whether life ever blossoms there. And that's a reminder that even in the vastness of space, the smallest details like a star's magnetic heartbeat can make all the difference. Now let's zoom out to the grandest scale of all, the universe itself. Magnetic fields aren't just local players, they might be one of the original architects of everything we see. From the moment of the Big Bang, these invisible forces could have been weaving the cosmic web, shaping galaxies, and even leaving fingerprints in the afterglow of creation. Take the LOFAR telescope, a sprawling network of antennas across Europe, designed to detect the faintest whispers of the universe's magnetic past. What it's revealing is astonishing. Magnetic fields appear to thread through the vast voids between galaxy clusters, like invisible highways stretching billions of light years. These aren't just random wrinkles in space, they're remnants of primordial fields, possibly dating back to the universe's first moments. Here's the wild part: these ancient fields might have helped galaxies form in the first place. In the early universe, gravity alone couldn't explain how matter clumped together so quickly. But add magnetism to the mix, and suddenly you have a cosmic scaffold, a network of forces nudging gas and dust into the dense knots that became the first stars and galaxies. Picture a river carving a canyon over eons, except here, magnetic fields sculpted the universe's structure on a timescale we can barely fathom. Even the cosmic microwave background, the oldest light in the universe, might hold clues. Some theories suggest that subtle twists in this radiation, its polarization, could betray the presence of primordial magnetic fields. If true, it would mean magnetism was there from the beginning, quietly guiding the universe's growth like an unseen hand. And the implications, they're staggering. If magnetic fields helped build the cosmos, they're not just features of the universe, they're foundational. From the largest galaxy clusters to the smallest star-forming clouds, magnetism might be the common thread tying it all together. Future telescopes like the Square Kilometre Array will dig even deeper into this mystery. By mapping the universe's magnetic skeleton with unprecedented precision, we might finally answer one of cosmology's biggest questions: did magnetism shape the universe as we know it? For now, the evidence points to a cosmos where magnetic fields aren't just part of the story, they might be the blueprint. So when you look up at the night sky, remember, what you're seeing isn't just stars and galaxies. It's a tapestry woven by invisible forces, a masterpiece billions of years in the making, and magnetism, it could be the thread holding it all together. As we bring this cosmic journey to a close, let's take a moment to marvel at the incredible symphony of magnetic forces that shape our universe. From the humble compass needle pointing north to the colossal jets screaming out of black holes at nearly the speed of light, magnetism weaves its invisible threads through every scale of existence. Think about it: these fields guide newborn stars into being, shield planets from deadly solar storms, and even sculpt the grand spiral arms of galaxies. They're the universe's silent choreographers, orchestrating the dance of matter and energy across billions of light years. And what's truly breathtaking is how much we've yet to uncover. Instruments like the Square Kilometre Array will soon peer deeper into the magnetic fabric of the cosmos, potentially revealing secrets about the universe's earliest moments. Could primordial magnetism explain why galaxies cluster the way they do? Might it hold clues to the nature of dark matter or the birth of the first stars? The possibilities are as vast as the fields themselves, so here's where you come in. Which of these magnetic marvels left you awestruck? Was it the way Earth's magnetic shield guards us from solar fury, or the mind-bending power of magnetars twisting spacetime itself? Drop your favorite in the comments. We'd love to hear what sparks your cosmic curiosity. And if you enjoyed this deep dive into the universe's hidden forces, don't forget to hit like, subscribe, and ring that notification bell so you never miss out on the next celestial adventure. The cosmos is full of mysteries waiting to be unraveled, and together we'll keep exploring the invisible forces that shape everything. Until next time, keep looking up, and remember, the universe's greatest stories are often written in magnetism's invisible ink.